introductions, I suppose. I'm Don. Some of you know me. Some may have never seen me before and wonder who is this strange grey-haired person. I'm currently doing a PhD at York University. I used to work for the Council for British Archaeology, but a very long time ago I started out at Sheffield University as a lithics person. And I did my first research degrees in stone tools and flint, and especially Yorkshire and East Midlands. And so I'm really here to give you an idea about everything lithics to do with, so that when you come across them in the course of your work with the Trust, you'll have a better idea of what you're looking at and how to identify things and what's man-made, what's not, what might be at different periods and so on. That's me. Okay, cool. So you've all got a wide range of backgrounds. You're coming at this for a whole range of different reasons. So I'm going to give you quite a wide-ranging sort of introduction to lithics here, so that hopefully you should all have something you can take away and use wherever you are. Okay, so first things first. Has anyone here done geology at all? Right. To what level?
First year university.
Okay, that's cool. For everyone else, geology is a strange land. Yes? Okay, because that's where we need to start. I need to start you with the perspective of someone living in the past in prehistory and why stone tools are so important. In a city like York, there's so much historic stuff. You tend to forget that 95% of human existence was before the historic period, when most people had to live off what they could get from the natural world around them. And so you can't do much in the way of anything to live without the ability to cut things down, to shape things, to scrape things, to grind things, to pierce things, etc. So you need tools to do all of this, and it's fairly straightforward. But what tools do you use, and how do you get the stone you need to make those tools? Because stone isn't just available everywhere. The geology of the UK is quite unique, really, for most parts of the world. The UK has everything from the most recent geological strata going right back to over 1,000 million years, and some of the very oldest, and we have a huge variety. Some other parts of the world don't, and they're very mono culture in terms of geology. So in Britain, we're just going to start with a basic introduction to some basic geology, so we know where we're coming from on all this. So, how do rocks form? You'll all be familiar with the idea that the centre of the Earth is fairly molten, or at least there are molten bits within the Earth, in the Earth's mantle and the Earth's crust. There are three types of rock that you need to be aware of. There are igneous rocks, which are those that solidify from molten lava. It's called magma when it's in the crust. When it erupts in a volcano at the surface, it's called lava. It's the same stuff. As the lava or magma cools down, the minerals within it will crystallise into small crystals. The lava that crystallises at the surface after a volcanic eruption crystallise very quickly. The crystals that form don't have time to form into any big size. They're quite small. So small interlocking crystals, very fine-grained rock that is produced. The rock that solidifies within the crust solidifies slowly. It has time for the crystals to form to a big size. So you get a rock with very obvious crystals you can see with the naked eye. So, rock in the crust, typical in Britain, would be granite. Granite is a very, very hard rock, formed of interlocking crystals of quartz, of a mineral called feldspar, which is a mixture of potassium, sodium, calcium and aluminium silicates, and various small amounts of minerals rich in iron and magnesium. You don't really need to know that, but you need to be aware that very, very strong rock, very, very hard, but full of large, obvious crystals that you can see with the naked eye. Typical of rocks formed at the surface, the fine-grained ones, would be a rock like basalt, or a rock called a rhyolite, R-H-Y-O-L-I-T-E, rather commoner in Britain than basalts. You can't see the crystals with the naked eye, only with a microscope, so they appear smooth. They tend to be dark. Basalt is usually a very dark brown or black colour, but weathers to a more sandy grey colour. And the thing about igneous rocks of the fine grain type, they do weather into much lighter colours and they can fool you into other things. So that's igneous rocks. Very straightforward, produce nice, hard, very resistant rocks. And you might think, oh yes, that's really useful. You can't really do much with the granite. the crystals are so big, if you try and shape it or flake it, the crystals will interfere with your edges, right? So they don't produce nice sharp edges, and the crystals will pound out and what have you, and granite is not an easy rock to use, so we tend to put that to one side. Rhyolites and basalts, yes, they're quite nice. You can shape them into nice sharp edges, but they're so hard it takes a huge amount of effort to do that. Okay, so igneous rocks, yeah, they're nice, but not as useful as they could be. Rocks at the surface will be subjected to all kinds of weathering. This is quite important. Frost and frost action, freezing and thawing in winter, with ice getting in cracks, pulling the rock apart. Rainwater is a chemical solution and contains various acids and alkalis which will attack different types of minerals in rock. Rock is subjected to basically fungi and bacteria and algae on the surface, which all help to eat up the surface and erode it. So it's a huge lots of process of erosion going on. Rocks at the surface will erode, they will break down, their constituent minerals will be released, and some of those minerals will then be changed into other minerals. And they'll be sluiced away in the rivers and the streams, and they'll be deposited off riverbanks and down in the oceans and the seas and in lakes. And over millions of years you'll get these layers of sediment building up, and the sediment will concrete into rocks. Right? So basically sedimentary rocks. Your main types of sedimentary rock: sandstone. Grains of quartz that are the quartz grains in the rocks that have been broken down, ground down into small round or sub-rounded particles and cemented together. Your other minerals in the rocks tend to break down into other things. So I mentioned feldspars and minerals rich in iron and magnesium in the granite. Under weathering, they turn into clay minerals. They lose a lot of their iron and magnesium and potassium and calcium, and they just become aluminium and silicates together. They're soft, flat, plate-like minerals. And they will clump together to form mudstones and shales. Quite soft rocks, which tend to break in sort of layers, because the minerals tend to align flat with each other. In between sandstones and shales, you'll get all sorts of rocks in between. Mixtures of the two. Rocks which are quite coarse grained, siltstones, to the very fine grained mudstones and really fine shales. Some of these rocks are very, very useful. The problem with shales is that although you can shape them easily, they're very soft. They have no resilience. You can make an edge on them, but the edge crumbles, you can't use it. So, not too good. Sandstones, on the other hand, full of nice, gritty, sharp quartz grains. And if the sandstones are nice and well cemented together, they're great for making, you've guessed it, things for grinding. Grinding stones, querns, that kind of thing. Now, you've got your igneous rocks, you've got your sedimentary rocks. What comes next? There's a third category. These are called the metamorphic rocks. These are rocks which have been subjected to pressure or temperature at the Earth's surface or within the crust. You probably all know that the Earth's surface isn't just still and benign. It's divided into various big, huge continental-sized plates that move slowly against each other. You have earthquakes, which move one bit of the land down, another bit up, a bit goes above, you get pressure, blah, blah, blah. So you get high temperatures and pressures when rocks are underneath other rocks and within the crust being subject to the movement of the Earth's crust. High temperature and pressure can effectively alter the minerals and melt the minerals and reform the rock into other rocks. Sedimentary rocks, when they reform, are quite straightforward. Sandstone will reform into quartzite. It'll be sand grains, quartz grains, cemented together by quartz in between. It's a huge quartz rock, very, very hard, much smoother than the original quartzite. Mudstones and shales, because they're formed of flat plate-like minerals, when they're squeezed under high temperature and pressure, they form slate. Right? So it's metamorphosed shales and mudstones, all nice and fissile, so they break easily along edges, nice and fine and straightforward. There's another type of sedimentary rock I've not mentioned, which is hugely important. It's a type of sedimentary rock that's formed mostly in the oceans, And if you think of oceans and what they contain, seawater contains a lot of dissolved minerals, such as calcium. It also contains a lot of animals and life, a lot of microscopic life especially. And a lot of that microscopic life has various skeletons and parts to it, formed either of calcium carbonate or of silica. There are special microscopic organisms related to bacteria called radiolaria that have silica skeletons. Remember that for the future. Other ones, like foraminifera, coccoliths and so on, which are a form of algae, have skeletons made of calcium carbonate, which they've taken from the seawater. So they've taken calcium, carbon dioxide out of the seawater and the air and made their skeletons. When these animals die, their skeletons just rain down onto the seafloor. And if it's a special type of sea where there's not much land sediment coming in, you'll end up with a sedimentary rock that's formed just of calcium carbonate. Right? So limestone. If you subject limestone to temperature and pressure as a metamorphic rock, you get marble. Now the term marble is used by artists to mean any decorative rock. A geologist has a very specific meaning for marble that's quite different. It's a metamorphosed limestone that's almost pure calcium carbonate that's been welded together. Right, so limestones, hugely important, because it's in limestone that our main rock that we're interested in forms, which is chert and flint. Now, here I come to the main thing on the menu. That's the hors d'oeuvre. This is the main course. Right. Flint, lovely flint. I like flint. Some people don't. Poor people. Flint is incredibly useful for various reasons. And its relative, chert, and other relatives that exist, which I'll talk about shortly. To have a stone that's useful for making usable tools, you need quite contradictory qualities. You need it to be hard, but you need it to be workable so you can shape it. So it can't be too hard. It must take a nice sharp edge, but in order to be workable, it also has to be quite brittle at the same time. So it's a conflict of different sort of qualities. Flint has those qualities in abundance. I've talked about quartz and silica a lot. So here we go. Chert and flint is mostly silica. Silica is a mineral formed of silicon atom surrounded by oxygen atoms. And the way it's structured is that it's like a three-dimensional lattice going off in all directions. And the way that you're taught in geology is that it's about the silica tetrahedron. Oxygen atom in the middle with silicon atoms at the four corners of the pyramid, and those just extend in 3 dimensions of the lattice. It makes it immensely strong. But as a lattice, it has flaws in it every so often. It's not perfect. And those flaws are what allow you to shape it. Okay, so that's important. Now, flint is not the only mineral that's made of silica. Right, so here I'm going to run through a few others, and I have to refer to notes. Believe me, it's 30 years since I looked at these notes, and I'd forgotten how much I'd forgotten. So, basically, these minerals form by replacing bits of limestone or being deposited in cavities inside the limestone. Now, why might you get cavities inside a limestone? Well, amongst the limestone forming on the seabed, you're going to get animals falling in and dying and being fossilised. Those animals' parts will eventually rot and disappear, and sometimes you're left with cavities inside the limestone. Sometimes you will find the limestone being burrowed into by animals as soft sediment on the sea floor, and those burrows will be full of soft sediment, which can easily just leach out and be eroded away, and you're left with cavities in the rock. Right, so, when you get water coming through, you think of it like a cave, and it's the reverse way round. Water comes through into a cave, precipitates out calcium carbonate, and you get stalagmites. Think of it the other way, because the chemical environment is very different. In chalk or limestone that's formed with cavities, water is percolating through that's rich in silica, and the silica precipitates out. Right? Now, when that happens, you're likely to get a type of mineral called chalcedony. Silica-rich, forms in cavities, very fibrous in structure, with a lot of separate gaps in it, pores. Chalcedony is okay, but it's not brilliant to use. Instead, what you would get, if you get sediment within the chalk that's softer than the surrounding chalk, like in a burrow, you get a complex chemical equation being set up, where there's a balance in the water that's in the sediment. Sometimes that water will be very rich in silica and becomes like almost a silicic acid. That can attack and eat and destroy calcium carbonate, so it disappears. But if the balance is just right, the amount of calcium carbonate gets into solution and the silica doesn't like it, and the silica goes, oh God, I'm getting out of here, and the silica precipitates out. So you get a delicate chemical balance where, like in an animal burrow, the soft limestone inside, the harder limestone around the outside, is being eaten away and it's being replaced by silica. So it's sort of like a particle by particle replacement of the calcium carbonate by silica. Now that's when you get chert and flint forming. So, what's the difference between chert and flint? Very simple. Limestone is a gradation of different kinds of sediment. There's some coarse limestone, which is full of all sorts of impurities. And if you go to the Peak District, outside Sheffield or in the Yorkshire Dales, you'll find lots and lots of lovely limestones, whitish, greyish, some dark grey, some light grey. The grey fraction is bits of land sediment that have come into the sea. They're bits of clay minerals or other minerals. It's impure. It's not a pure limestone. Remember, the silica that's precipitating out is only replacing the calcium carbonate. So it's still containing all the little impurities. Now, go to the Yorkshire Wolds and think of the chalk. Chalk is just a limestone, but it's a very, very pure limestone. There is very little land-based sediment getting into the sea. So the silica that replaced the chalk is very pure. That's basically the difference. Flint is a very, very pure form of chert. And strictly speaking, we should call it all chert. That should be the generic name of it. But flint is a very pure form. You can get cherts that are very flint-like. You can get flints that are very chert-like. There's a sort of gradation between them. Okay? Now, some of the impurities that get into the chert or the chalcedony can be very important. They give you colours. So iron impurities, iron minerals that happen to be lying around there, will tend to give a very red colour to any chert or flint. When you get a very red form of chalcedony, you get something which we call jasper. Very important in southwest Scotland, when they don't have good supplies of flint, but they do have bloodstone, which is a form of jasper on the Isle of Rum, which is used intensively for making stone tools. Other colours, different kinds of impurities, and we'll come across those later. Now, in terms of microscopic structure, chert and flint all has basically very, very, very small crystallites, microscopic crystals of quartz. These are sort of 1/10 of 1,000th of a millimetre in size, so about 1/10 of a micron. They're tiny. But they clump together into scales, which are about 1 micron in size. In between the scales are gaps which are filled with water. Right, so quartz, silica clumps with pores in between. The pores in flint tend to interconnect. They're your lines of weakness which allow you to flake it and shape it. Okay? That structure is important when we come along later to talk about how you can alter flint and make it more knappable by heating it. Any questions so far? Right? You're not snoring yet. Brilliant, brilliant. Okay, right. That's a bit of boring background, but it's fairly important background. Without understanding all that, you won't understand why people use flint in the first place, and how you can use it and how you can alter it, and where it occurs. So, in terms of where chert and flint occur, so we need limestone. So it's not going to occur everywhere. Where are the major deposits of limestone? I've already mentioned some. Peak District in the Yorkshire Dales. The Yorkshire Wolds. Any others you can think of? Lake District, there are some, yes. Anywhere else? Welcome.
Really sorry.
That's all right.
We were, we looked at the wrong information about the
Oh,
location of today's.
so you've been to Harrogate and back.
More of one day.
That's all right. You've missed the boring bit. It's fine. It's okay.
Just our camera angles now.
Right.
If you three sit on there, I'll
People in the shots.
Just come on in.
Right.
I'll wait till you get settled and then you're fine. All right. Oh, heck, you're taller than me. Bloody hell. I'm not used to this.
Switch down.
Yeah. Right. Okay, so we're talking about where limestone exists then. So we've got Peak District, the Lake District, as you've mentioned, Yorkshire Dales, Yorkshire Wolds, anywhere else we can think of in the north of England or the Midlands where there is limestone. Anyone here been to Creswell Crags? Yeah? A spine of limestone that's running north-south through Nottinghamshire, Derbyshire into South Yorkshire. Would you find flint and chert in there? You think, oh, it's a limestone, there must be. No, you won't. Because that limestone has undergone a process since it was deposited 250 million years ago, which has effectively recrystallised it. It's semi-metamorphized, or metamorphosed, I should say. So that a lot of the calcium carbonate in that limestone has been replaced by magnesium carbonate. Calcium magnesium atoms are very similar in size. The magnesium knocks out a calcium and takes over the carbonate. Right? Because it's done that, it's recrystallised the whole thing. Because it's now a largely magnesium carbonate body, silica doesn't do the same thing it does to calcium. It won't replace it with chert and flint. You won't find chert and flint in magnesian limestone, which is what that is called. So that you have to ignore that. So in terms of the north of England, your chert flint sources are on either side of the Vale of York. Right? So in the Pennines and the Yorkshire Wolds. Right? So within the limestone, flint will form within the gaps and the spaces which are full of the soft bits of sediment within the harder surrounding chalk. Now that can either be little individual cavities, which what might have once been a fossil that is now gone and is just a cavity in the chalk. It can be the animal burrows, which are a bit like rabbit burrows going off in all directions. It can be the layers in between bits of chalk, which have been pulled apart. So you'll get flint which forms as discrete nodules, you'll get flint which forms as large interconnecting masses, and you get flint which is formed as sheets, horizontal sheets. And it's the same with the chert in the limestone. So we've gone through that. Now it's time to look at, I'm sorry I don't have copies of this. I only found this late yesterday. I'd forgotten I had it. Geological map, right, north of England. One of the first things I would do if I'm going into an area to find out where sources of flint might be would be to get hold of a geological map. There are two sorts of geological map. There are those which show you the bedrock, and there are those which are called drift maps, which show you the soft deposits of more modern glacial, lake-borne and riverine and oceanic deposits which cover the bedrock. It's the drift maps that you need, for reasons I will come on to shortly. So, on here, you can't really see this, I apologise, I'll pass it round for you to look at. The brickwork patterns are the limestone and the chalk. Right. The black shading are glacial boulder clay deposits or till deposits. Right. Now that's quite important. I'll pass that around, you can just have a look and circulate around. So, we're getting an idea of where people in the past might have had access to flint and chalk, to flint and chert. Obviously there are rivers now which are eroding some of these deposits, so you might expect to find river cobbles of chert and flint coming into areas from places where there are limestones. We also have the glaciers. Glaciers are important. They scrape up rock and transport rock from one place to another. Fortunately for us, The glaciers that hit the north of England were coming in from a northeasterly direction across the North Sea. In the North Sea there are chalk deposits, and they brought flint with them from that chalk and deposited it into the north of England. Why is that important? Because we've got chalk already in the north of England, in the Yorkshire Wolds. Well, very simple. The chalk in the Yorkshire Wolds, I don't have a cobble on it, I only have small flakes of it. The chalk in the Yorkshire Wolds is absolutely horrific stuff. It's horrible. It looks like, this is a simple flake of it, it looks like that. It's white and opaque. It doesn't look like what you think of as flint. If you go down to Grimes Graves in Norfolk, you'll find nice black shiny flint. You will not find flint like that in the chalk of the Yorkshire Wolds. And the reason is that way back in 100 million years ago, when that was a sea with dead coccoliths raining down with its calcium carbonate skeletons onto the sea floor, it was receiving a different set of ocean currents from different continents. They were technically different seas at the time. So the structure of the chalk in the north of England, anywhere from the Wash northwards, is actually much coarser than the structure of the chalk from the Wash southwards. And as flint is a replacement of the chalk, particle by particle, the flint in it is also much coarser. So the flint from the north is horrible white stuff. Fortunately for us, the flint that came in with the glaciers from the rest of the North Sea just happened to belong to that southern flint chalk province. Somehow that southern chalk province actually makes a turn up to the north once you get out into the ocean. So we get this stuff is all from the glacial tills. And that's where 95% of most of the flint used in this part of the world comes from, rather than the chalk. You will find chalk being used, the chalk flint being used for stone tools, in parts of the Mesolithic and the Paleolithic. You might occasionally come across a little bit of it in the late Mesolithic and Neolithic and Early Bronze Age, but really most of the stuff you're coming across should be from the till deposits, right, rather than the chalk. Major difference between what's going on here and what's going in the south of England. In the south of England you have flint mines, Neolithic and Early Bronze Age, mostly Neolithic. Grimes Graves is different because it carries on into the Early Bronze Age. There are possibly around about 20 or so flint mines in the south of England. You don't get any flint mines in the north. Right, so we've covered that. That's quite important. Now, I'll talk about that in a minute. So, you've got your flint. It's formed in the chalk. Is that it then? Does it just stay like that? Well, no. Remember that flint is at a microscopic level, tiny particles and clumps about 1 micron in size of quartz crystals with gaps in between full of water and other impurities. When you see flint coming out of the chalk, you'll often see it with a white skin around it. You've all seen that, flint with a white skin. What do you think that white skin is? Any ideas?
Is it impurity leaching out?
Oh, I like you. Not bad. You may be tall, but you're okay. All right. It's basically what happens is that the surface of the flint at a microscopic level is leaching out the water and the impurities from the pores. So you're getting a flint which is becoming denatured, where you're just getting the quartz clumps and they're losing the binding between them. That makes it more friable. It also makes it sort of, if you like, more rough and pitted, and what it's doing is it's reflecting light back at you, which is why it's appearing to be white. Okay? So that's called the cortex. People who don't know about flint think the cortex is a mixture of chalk and flint, and it's not, because it looks quite chalky. Okay? Now, that cortex forms on the flint when it's still in the chalk. It can also form on the flint once it's come out of the chalk and once it's in an archaeological context. So you distinguish between primary cortex, the cortex on the flint as it comes out of the chalk, and the secondary cortex, which forms in more archaeological contexts. How does that leaching out of the water happen and that pitting of the surface of the quartz? It's because the surface of the flint is being attacked by chemicals in the water that comes into contact with it. Either strong alkalines or carbonic acids, basically organic acids, plant roots in the soil, for example. You can sometimes find flints with streaks, white and bluish streaks on the surface, which are where plant roots have been in contact with the flake or the flint. And those plant roots are secreting acids which are eating away the surface of the flint. That's basically what's happening. Also, it depends on the soils. Things like soils rich in sodium, for example, can knock out the calcium from calcium carbonate and have an effect on leaching out and attacking the quartz flints. So you get secondary cortex can be formed. This is what archaeology will often call patination. Technically, patination is something a bit different. You'll find flints which come from an archaeological context. Yes, this has a nice bit of secondary cortication on it. I like this whitish stuff. But you'll also notice it's rather glossy. Right, it has that typical glossy sheen to it that archaeological flints have. Whereas this one, which is just straight from the chalk, doesn't. That's a dull matte colour. Right? Flint naturally doesn't have that high sheen, that high gloss polish that you often see. That gloss is an incomplete process of cortication. The surface has been eaten away, but all the stuff that's eaten away is then being redeposited on the surface. It's a very complicated process of chemical smoothing of the surface of the flint. So you don't get individual quartz grains clumps sticking up. They're all smoothed out. And you get this knocking out of quartz from the quartz clumps, and they've been deposited in the pores in between them. So you get this smooth surface, which reflects light back as a smooth sort of reflection. So that's technically patination, a chemical polishing of the surface. The other process you can get that's active in flint is staining. And you'll quite often see this in flints which have been in the river, or streams and what have you, or bogs and marshes. If the surface of the flint is roughened and corticated, it can easily take and attach manganese or iron or other impurities which will colour it. The commonest one is the red coloration. You might get a reddish brown, which is iron impurities being attached onto the surface of the flint. Sometimes those iron impurities are formed and taken within the flint itself because they were present in the original limestone, and in which case you get a reddish brown flint. And that's natural. That's the original colour of the flint. So that's sometimes there as well. And you will find a proportion of a beautiful brown, reddish brown flint in amongst the tills on the Yorkshire coast. Right. So that's staining, cortication, patination. The other thing that you can do is to heat the flint. Now, flint, when it's subject to heating, also does some rather interesting things. Why might you want to heat the flint? Any ideas?
The expansion of the water layers to make it split better.
Ooh, interesting idea. You could do that, and in fact, modern times, people have heated and calcined flint to make it break up,
Yeah,
to use it as a grog, as a filler in pottery. In prehistoric times, no, that's not the case. But in modern historic times, yes, you will find that. And in fact, what happens there is as you heat the flint, if you heat it to above, and I think it's above 350 degrees centigrade, the water in the pores turns to steam, to vapour. And the vapour pressure is something like 1,600 pounds per square inch. And the flint goes and basically explodes from the inside. right? So it shatters. So that's one thing you can do. I'm just thinking, I don't think I brought my nice little one of, no, damn. Okay. One of the main reasons you might do this in prehistory is very simple. If you heat flint to just below 350 degrees centigrade, but above about 300, it's a sort of narrow band, what happens is that the impurities in the water, in the pores between the quartz clumps, scales, the impurities acts as what's called a flux, which lowers the melting point of the surface of the quartz grains. And the quartz grains start to melt and fuse together. The water gets driven off and the quartz grains start to fuse together and the pores get smaller and smaller. The flint becomes more homogeneous. But also, because of the nature of quartz as a mineral, the way the quartz is structured is that it is not equal in all directions. It has a preferred symmetry, and it will expand as it's heated in one direction rather more than it heats in the other direction. So it sets up stresses internally, and those stresses can lead to microfractures at a very, very microscopic scale, which means that it actually becomes easier to flake. So you're making a more homogeneous material that's easier to flake. And if you want to do something like make nice, lovely arrowheads, heat treating the flint is one way of making it much, much easier to make. Okay? And we know from ethnographic examples that people did heat treat flint. North America, for example, there are reports of people heat treating flint. How might you, do you think, heat treat flint to make it improved? What might you do? Are you just going to bung it in the fire?
You boil it in water or something?
Not in water. You have to think in a different way. We're not used to thinking in this way of how you do things. You dig a little shallow pit in the ground, but you put your flints in this pit, you cover them with sand or some soil, you build a bonfire on top of them. And the heat from the bonfire percolates through the soil into the flint below and gently heats them up. And the way the North American Indians did it was that they had a rough idea of how long it had gone on, and looking at the colour of the flames and how much wood they put on, etc., they could roughly gauge how long they needed and what temperature it was getting to. And they could do it so they got the flint just right. So a little shallow scoop flint underneath. We don't know that's how they did it in prehistory here, but that's certainly one effective way of doing it. Now I did this in a laboratory back in Sheffield. I put them in a heat tray full of soil, put some flakes, and after heating them, I was pressure flaking. I'll talk about pressure flaking later. The flakes I was able to take off were about 6 times as long as the flakes I could take off without heat treating. Right? So it really is very, very effective. The problem with heat treating is that you can go too far, and the flint will shatter and break. And you will find calcined, broken, shattered, frost fractured or heat fractured flints on a site. You'll find them crazed with like crazing, look on like crazed porcelain, and they'll go white. Right? Because it's driving off the water, cracking the surface, and it's reflecting all the light back here. So you get heat cracked flints on sites. Now this may be heat treatment that's gone wrong. It may just be they've been using flint in amongst other things to boil water, pot boilers. It may be that flint has accidentally been under a hearth, but it might be deliberate. You can't just assume it's not natural. It might be from heat treatment that's gone wrong. That's more likely if it's flakes that look as though they've been heat treated before they've been retouched. So if you just get a flake of flint that's crazed and has had no flakes taken off it, it might have been they've been heat treating a blank to try and make it easier to make a tool out of. Right? So the other thing about heat treatment is that if you do it right, because the quartz has fused together, it's now very, very smooth. The flake scars that come off it are intensely glossy, very, very shiny. Heat-treated flint is much glossier in appearance than non-heat-treated flint. So you can sometimes tell when a thing has been heat treated. But it's very hard to tell that apart from the patination that it acquires in the soil through that chemical polishing in the surface. Okay, so you've got a problem there. If you have a piece of flint with different scars on it, some of which are slightly glossy, some which are intensely very, very, very glossy, then I think you can be sure you've got evidence of heat treatment from those very, very glossy scars that stand out against the background of the rest of it. Okay, so that's important heat treatment stuff, quite important. So we've gone through all that. Oh yes, we've gone through colour, water content. Right, okay, so let's now think about flint and making tools. Oh, check the time. Oh, okay, right, okay. I'm going to give you a short break so I don't bore you to death all the way through this, okay? So you can have a chance to stretch your legs. Right, so that's our sort of basic introduction. So you will have flint occurring in the area in a natural form. In its natural form, it will occur as broken cobbles within the rivers, as small cobbles on the beach. The best place to get flint in the whole of the north of England is to go to Holderness, anywhere between Bridlington down to Spurn Point, and just go on the beach, and you will find tons of flint like this. Nice and flattish, which is what you want. Often when people go and, collect flint to try and use, they will go for fairly rounded cobbles and things which seem to be quite big. That's not what you want. You want nice flattish bits, and that will come on to why later. The problem with the beach flint is because it's on the beach, it's being pounded by the waves and it's knocking against other cobbles all the time, and a lot of beach flint is actually fractured inside and broken from that pounding by the waves. Now you might think, well, why not just go to the Boulder Clay Cliffs and hoik it out of the Boulder Clay Cliffs? You can do that, but there's not a huge amount of it appearing in the cliffs. It's being sorted out onto the beach already for you and concentrated in amount. And also trying to get it out of the Boulder Clay Cliffs isn't always that easy. I remember back in the 1980s going there with Marek Zvelobil to have a look at getting some flint, and Marek saw this flint about this big, this round. He wanted this out of the cliff. 2 hours later, with metal bars, he still failed. The clay in the boulder clay is really hard stuff and sticky and horrible. You can spend a huge amount of time and effort trying to get stuff out of those cliffs and fail miserably. Right? We had to leave it behind. He was nearly crying. Go down to the beach and just pick it up off the beach. It's far, far easier. Inland, your flint is going to occur up the Hull estuary, in the sediments on the riverside, and in the rivers that drain the boulder clays into the Trent and the River Trent. You'll get a little bit of flint in the northern bit of the Vale of York, where you get bits of boulder clay coming in that have come off the North Sea, and there'll be a bit draining that way. There are supposed to be flint in, and I've never researched this, but on the other side of the Pennines in the sort of Cheshire Plain, Lancashire area, which have again been brought by boulder clays off the sea and dumped on land. But basically you're looking at a sort of easterly and southeasterly distribution of where flint naturally occurs. Whether there's any flint occurring naturally in the glacial sediments of this part of the Vale of York is something I don't know because I've never researched it. But you might want to have a look at researching some of the geological monographs about the till deposits in the Vale of York to see whether they contain any natural flint. If not, then any flint you find here has got to come from to the east or southeast of here. Okay, that's quite important in itself. Let's start thinking now about how flint and chert is used in the prehistoric period for making tools and the whole sort of process and everything that we need to think about. So let's begin by thinking about what are the actual uses for stone and tools in the prehistoric period. Can you tell me what uses you think there are?
Scraping things.
Scraping things?
Arrows, shooting things.
Shooting things?
Cutting.
Cutting things?
Making really interesting wooden artifacts.
Yes, making really interesting wooden artifacts. Absolutely, yep. Woodworking, yep. Anything else?
Timber and pottery, we already
Yeah,
said.
temporary, what we said? Cooking.
Sewing, kind of like forgotten the word now. Piercing things.
Piercing things.
Like trade goods, perhaps.
Trade goods. Oh, good man. Okay, so I don't have copies of this, but think of it in your minds as like a diagram. So we have stone tools. We have utilitarian uses and we have social uses. Okay, so you've got to think of it, split it up into those two for a start. So utilitarian uses, you have striking things, axes, hammers, chisels, things like that, right? You have cutting, so knives, sickles, saws, piercing things, so awls, piercers, daggers, arrows, right? Things that pierce, and scraping. So striking, cutting, piercing, scraping, those are your 4 basic actions that you need stone tools for. Social purposes of stone tools. Exchange as a trade good. Yes, there are people around who haven't got flint who would like it. So that's a commodity you've got to exchange for something. It can be a form of display as well. If you ever go to Denmark, I recommend you go to the National Museum in Copenhagen. If you do, you will end up doing what I did when I was there a couple of years ago, and you'll develop a severe case of Tourette's syndrome. You'll walk into the gallery and go, oh, fuck. Because you will see the best flint work ever made. The early Bronze Age in Denmark made whole swords in one piece of flint, this big. You can't use them. They're purely for display. They made daggers in flint, one piece, with the handle carved out of the flint, with the seams of the leather on the handle carved in the flint, and the rivets carved in the flint. Absolutely phenomenal. Totally display-oriented artifacts, beyond belief. You don't get anything that good in Britain, but you do get artifacts made purely for show out of flint. And I'll come on to what those might be slightly later. So display, and also as a form of wealth. You know, flint is a valuable commodity. You have it, other people don't. That makes you wealthy. Or you have a skill as a napper. That makes you highly sought after. Right? So think about that social side of things as well as the utilitarian. Now, when it comes to actually making stone tools, you have your piece of flint, you need to bash it in some way, right, to knock bits off. It's a reductive technology. You're reducing bits, taking bits off. You need a stone, a hammer stone. Wherever you have knapping, you should have hammer stones. Hammer stones like this one, this is the one I used to use in the 80s. Yes, I am that old. I know I don't look it, but yes. Abraded. You'll see the signs of abrasion and wear on the edges, and that's something you should be looking out for. Right. Sometimes a hammer stone will break, and you'll find them in half as well. But they will also have the telltale abrasion and wear. The abrasion is fairly easy to spot on this one, less easy to spot on this one because it's a slightly different type of rock, but it is there, right, on the ends, very abraded. So I'll pass them round so you can see what the abrasion looks like. So the basic technique is very, very simple. You have a flint cobble. That cobble can itself be turned into an artifact, or it can be your source of raw material for making artifacts. So by striking bits off it, you can then make tools out of the bits that come off it. So you have core tools. The bits that come off are flakes. They're flake tools. Right? In the Paleolithic, everyone concentrates on making hand axes when they replicate making stone tools. Those are core tools. Axes are core tools. Even in the Paleolithic, the vast majority of tools they used actually would have been flake tools, not the cores. Cores are mostly your source of material. So, Anne, can I have that one in your right hand there for a moment? Thanks. So, the process is to hit one with the other. Oh, I love that sound. It's a great sound. I love it. Just the sound. Yeah, I could do this all day. And I can hit away and nothing's going to happen. I can hit this really harder and nothing's going to happen at all. Most people, when they start trying to make stone tools, they'll bash rocks together and nothing happens. You have to know how. Right? You have to know how flint fractures and the principles of fracture mechanics. And it's actually incredibly simple and straightforward. Go back to the microscopic structure of flint. Quartz scales with pores in between filled with water. There are natural flaws within that structure, gaps between the scales. If you hit something, there's a pressure wave coming through what it is you're hitting. That pressure wave will hit a gap between the flint scales and widen it. It'll then widen the next one behind it, and the next one, and the next one. And you'll have a crack gradually growing and creeping through the flint, which will come off. Right? So in order for that to work, the pressure wave that you're putting through the flint has to come down from the surface and make its way parallel to the face if you want to get a piece to come off. Or this way around, hitting it here for the pressure waves to come off. The trick about flint knapping is you're trying to get a flake off the side of it, not off the bottom of it. Right? So ideally what you need is a flat surface with a face that is coming off underneath it at 90 degrees or less. And that's what any napper is looking for, is an angle that's 90 degrees or better, less than 90 degrees, with a flat bit that they can hit. Now on this one, I might hit there or I might hit there. That angle is still less than 90 degrees. If you find an angle that's greater than 90 degrees, like on the rounded cobbles and pebbles, rounded surfaces, you can be going for hours and not get anything off. That's why you want flatter bits of cobble. You are looking for cobbles with those angles and faces on. Right? That makes sense. I've been debating whether to do this. I'm all right to just have a little nap.
Don't see why not.
Go on. Let me see if I can just get a flake off one of these. You might wish to move a little, Anne. I'm all right standing up. Let's see if I can get something off one of these. Having said all this, I'll probably fail miserably now to get anything off. That might be interesting. Oops. That one's going to be. Let me try something off here. All right. So that was just 2 taps, and I got a flake off the side. So that came off just there. What I was doing, I was deliberately attacking that bit because that bit was coming off underneath it. Okay, see that? So that then is what we call the platform of the core, and I'm hitting it to take bit off the side. So as you look at it there, so it's off that side, which actually falls off from underneath, and you get, can you see on this now, there's a difference in the appearance between that scar, which is where that flake was, and the rest of the surface there. This is slightly glossier. That's more of a matte sort of finish. It's what's technically called a horny lustre. You ever think of flint as horny? Well, it's, you know, right. That's the natural surface. That is that glossy patina, which I was talking about earlier, that patinated surface. That's the chemically altered surface. Okay, so I've got my one flake off, and that flake carries on the surface bits of the original outer surface of the cobble. And that is what you would know as a primary flake. It's the first flake taken off the face of a cobble, or that portion of the cobble that carries on its surface the outside of the cobble. Right. What I would then do is carry on napping that, or I would turn it over and hit that scar to take a flake off underneath. There are many ways of doing this. That's the basic thing. So I've got a piece off, and you'll notice that what comes off as well are little tiny bits and pieces. Because this is the first one coming off, the surface is quite friable and weathered anyway, so the flake won't come off perfectly. Some of it will break off as you nap it. Right? So I've got little tiny bits, some bigger bits, and little bits, and wherever you nap you get this shatter of tiny, tiny little bits of flint. Now I, being a first-class idiot, when I was a student, I used to nap in my bedsit in Sheffield, which was great fun. It meant I wasn't doing it outside, wasn't harming anyone, was everything, except when you come to go to bed at night and you take your socks off and you find your carpet is full of little tiny sherds and little tiny splinters of flint. And you wake up in the morning with blood stains all over your sheets as your feet have been cut to shreds. This small shatter that comes off goes down to really, really small levels. They were still napping flint well into the 19th century in Norfolk to make gun flints for muskets. The napping was so intense at Grimes Graves, where they were doing all this, in Thetford, in Norfolk, that a lot of the nappers were coming down with pneumoconiosis or silicosis. Their lungs are getting full of little tiny flakes of flint. You do this enough in a closed area, you're breathing in small, tiny amounts of flint. And a lot of the nappers in the 18th, 19th centuries weren't living that long. Right? So napping flint is actually dangerous. In this environment, it's no problem at all. Napping flint with the public is no problem at all. But don't do it every day for 10 years of your life, indoors. Right? Now, prehistoric flint working, probably going to happen outdoors, maybe inside a house, but it's not going to be on a mass industrial scale, even at Grimes Graves. So that may or may not have been something that prehistoric people were prone to. Who knows? Right, so let me give you now some handouts. I'm so old-fashioned, I love handouts. Right, so there's a whole pile here, some of which will be more useful than others. If you want to pass that one on, they're all together. There's one lot. You pass that lot on, and pass. Yep. There's plenty. Just keep passing around until they stop, until someone's got them, and then keep them. Okay. Yep.
The other sheet's gone. If you want to leave it with a copy, I can photocopy them and get
That's
them.
fine, thank you. That's absolutely fine. That's lovely. Okay. And one round. Oops. Okay. They want to come off more easily that way than the other way. Weird. Okay. That's it. There we are.
Just a tag, please.
Okay, there we are. Right. One more lot. Yep, that figures. That should be it. Right. Okay, so just look at the top sheet for the moment. That's all you need. So, diagram on the left. Top left, hammerstone hitting edge of flake. Stress waves coming out, concentric circles coming down. The result that comes off is a flake. And on that flake, if you hold it up to the side like that, you get what's on the middle on that left-hand side. Right? So you have a flake on its side. There are various terminology here that we use. Proximal. The proximal end of a flake is that bit which is the bit I hit. So it's the top bit of the flake. The distal part of the flake is the bit at the bottom opposite. Right? The dorsal side of the flake is this bit that was on the outside of the core. The ventral side of the flake was that bit that was on the inside of the core. Okay? Now, you will also notice that on the diagram there is what's called the bulb of percussion. You don't always get this on flakes, but on this one, yes, it's there. And if you look at the face diagram next to it, which is the same flake but looking on the ventral side, you'll notice that at the top there is something called a cone of percussion. This is where the hammerstone has hit the flake. And it leaves a little fracture, looks like a conical fracture at the top. And the stress waves then come out and they form a bulge as the fracture happens. It forms a little bulb and then it straightens out and goes to the edge of the flint. You also get something called the bulbous scar. This is where the stress waves are actually reflecting off the face of the core. So you've hit it, and the stress waves going down, but the stress waves going out as well. They hit the face of the core and they come back, and they take off part of the ventral face that's just detaching itself as a little, usually a slightly D-shaped scar. You then have what are called ripple marks. And those are the fluctuations in the wave front of the scar as it comes off of the fracture plane. We call those the ripple marks. We then have what I've labelled as fissures, which are towards the edge. And you can see they're little lines, and they're where the fracture plane is becoming a little bit unstable in one dimension. And they start to crack along the edge. Right? Those are all the features you need to tell you that something is humanly struck, as opposed to natural. Now, if you pass this one round, which I just struck off, you should see all those features on that. Okay. Now, when it comes to deciding between humanly struck and artificially struck, we may have problems. It's not always that easy. So, here are some genuine flints which I've collected from my travels over the years, which I know to be humanly struck, or I'm reasonably certain are humanly struck. And here are some which aren't. So, if you pass that one round, that will look superficially as though it's humanly struck. It has a flat bit which looks like a platform. It has a big bulb. It doesn't really have the bulbous scar, doesn't have a cone of percussion, doesn't have fissures, doesn't have ripples. But it has a bulb and a platform. Okay, so is that natural or not? Well, then you get ones like this. Bit of flint, it has hollow-shaped scoops on it. And you think, oh, that's like a redundant core. They've taken bits of flakes off that, and it's like the hollow bits that are left. Well, yeah, possibly, possibly not. Then you have bits like this. Lumps of flint which are quite flattish. Don't really have hollow bits, don't really have bulbs, but I've seen things like that people have labelled as artefacts. You have lumps of flint like this, which are obviously a small little cobble that's had bits that have come off it. And it's got secondary cortex, it's nice and glossy, and again I've seen people describe those as cores. Apart from that one flake which I struck off, all those are not humanly made. Those are natural in some way or other. Natural processes can mimic the human. In particular, frost action can expand the water in the pores of flint and ping off flakes from the surface of a flint cobble. What you will then find is something like that white one, which is that sort of, looks like a big bulb thing. That's a typical frost pot lid fracture. The bulb is more central and it's not coming down from the platform. Doesn't have the ripple marks, doesn't have the fissure lines, right? And has nothing on the flat bit to show it's been struck. Right? No cone of percussion. Again, the frost can just, if the flint is fairly coarse, it can produce quite flat, hackly fractures, which is what that is. That grey one going round, quite natural. The other white one, I think, is again mostly frost that's done that. Actually come off. Other things, river pebbles rolling around the riverbed as the stream's in flood, bashing against other cobbles, bits of shattering, bits of flake coming off, which I think is what the pseudo core is that was coming around. I think that's river shattered, bit of cobble. The other thing that can fool you is you can get very nice flake scars that form on pieces. These are really some nice flake scars on these. And if those were flint, they would be labelled as artefacts and as retouched. They're Guinness bottle glass. And they're picked up from fields in Ireland. When I was in the 80s, I was involved with Marix Vellabil on a project, field walking to find Neolithic and Mesolithic sites. We did shitloads of field walking. I shouldn't have said that in front of the camera, but never mind. And in amongst these ploughed fields were Guinness bottles. And the plough in the field has done all that retouching. That is a real problem with flint that's been collected from field walking. To be able to differentiate humanly from plough-worked flints. And it's not easy. It really isn't. Oops. So there are things that can fool you. Now, go back to our diagram. I just struck a flake off that with my favourite hammerstone. Not all hammerstones are made of stone. When you're trying to shape flint more finely, in a more refined way, you will want to use something like antler or a very hard, dense wood. That will give you a softer, wider pattern of stress, as it were, going through, pressure waves going through the flint. So it will make the flakes flatter as they come off. You may want to use the point of an antler tine. And if you're in the Bronze Age, you may want to put in the point of the tine a little bit of copper. So you have something like a nice finger that you can place on the edge of a flake and push small flakes off the flint. This is where you need heat treatment. Trying to pressure flake non-heat treated flint is really hard. It can be done. North American Indians had big chest crutches that they built out of wood with the flaking tool at the end, and they would lean on it and press flakes off obsidian and flint because they were using their whole body weight to get enough pressure to push flakes off the flint. If you heat treat it, you don't need to do that. You can easily pressure flake when you heat treat. And what you will find is that the type of flake you get off differs. So the bottom on the left, flakes with a very obvious bulb of percussion tend to be hard hammered flakes, stone hammer. If the bulb is really quite flat and diffuse, then it's more likely to be a soft hammered flake. Pressure flaking flakes are incredibly thin, and they really won't survive but if you, unless you do immense amounts of sieving, but they'll be very, very flat and very thin. So that's all fairly nice and fairly straightforward. You're making your tools and you're doing nice stuff. And let me see if I can find some nice ones. Okay. And if you're lucky, you can produce some very nice big flakes. Here's a big one. I've actually glued it back together because it split in half when it came off. Not all flakes are as big as this, but you can easily see the platform, you can see the bulb, you can see the riffle marks, especially towards the bottom. Stress fissures are just there, but almost. There's no real cone, but that's quite a nice little flake. Pass that one round. Here's another nice flake. And you get some really nice flakes with some nice edges you can use. And the ideal is to produce some nice sharp edges. However, flaking doesn't always go nicely. You can hit it too far in from the platform so that the pressure waves aren't near enough to the surface. They go down and inwards into the core, and they'll do one of two things. They'll either go that way and take off the bottom of the core, or they'll go, oh, I don't like this, I want to get out, and they reverse back on themselves and come out the face. And they don't produce a nice sharp edge at the end. So on here, what you have is what's called the hinge fracture on the top right, where you get a totally smooth semicircular end to the flake, such as on this. That's a beautiful hinge fracture. Right? This is one I did. It's one of my failures. And you get this sometimes with a lip there, sometimes not, but this totally smooth rolled over end, that is useless for making anything out of. You can't even retouch that because it's that sort of shape and you just can't do anything with it. It's absolutely rubbish. That's a hinge fracture. The opposite is the plunging fracture, where you take off the bottom of the core and you end up with a golf club. Right. Again, this is one of mine. Right. I angled my shot too much inwards to the core rather than outwards from the edge. So I was pushing the pressure wave inwards instead of parallel and outwards. Right. So you'll find examples of both of those on archaeological sites. They're napping failures. Not all prehistoric nappers were good. And if you think, how do you learn? It's been suggested from some flint scatters that we can see evidence of children napping. The size of the hammerstone, the size of the nodule, and the fact there's a lot of failures and mishits and things like that. So practicing napping. Oh yeah, that's right, okay. The other fracture that's very, very common is the step fracture. I haven't really got examples of those here, but it's very simple. The flake fails to detach from the core properly, and it breaks as it comes off, and you get this flat end across. Okay. You also, as the flake comes off the core, it can sometimes, depending on how you're holding the core, the bottom of it can actually crush against the face of the core. And you can get small amounts of retouching scars on the end of a flake, which are nothing to do with retouching, it's just where the end has been crushed as it's come off the core. Right. The other thing, again, I haven't got examples of, they're quite rare, these snap fractures. Sometimes you might actually deliberately want to snap a flint, and we'll come across later why you might want to do that. Sometimes it might snap in the process of use. And with a snap fracture, you get what I've illustrated here, which is this sort of concavity with a lip. And that lip is on the top side, and the fracture has come downwards from where the lip is. So it's snapped in that sort of direction. Although flint is strong, if you exert enough pressure in the wrong way, you can snap it. Snap fractures tend to be from use rather than bad napping. So, to summarise, you may have one of these somewhere, probably, or may not, who knows. If you haven't got one of these, don't worry. I can't remember now which, no, you haven't. Just look at this one then, that's fine. So, summarise, we have our cobble, we have our core from which flakes have been detached. From the flake, we then make various tools, or, I haven't really mentioned this yet, from blades we make various tools. The difference between a blade and a flake is very simple. Blades have long parallel sides. And they're at least, it depends on which archaeologist you talk to and which lithics expert you talk to, because it's not standardised. It's either 1.5 times the length than the width, or twice as long as it is wide. But the key is long parallel sided. They're deliberately made like that, and you can deliberately make a core to produce blades. Blades are really, really useful because they have a very long edge to the surface area of the flint. So you're maximising the cutting potential. In other words, where you have a low quantity of raw material, or where you have pressure to maximise your raw material because you might be highly mobile in the environment and you can carrying flint around you is very heavy, you will tend to produce blades. You maximise the usable flint per amount of flint you've got. Okay, so that's fairly straightforward. Now, I need to remind myself. Let's go to not the next sheet, I'm going to be sneaky, but the bottom 2 sheets. Which should be these ones. Okay. Right. So we've got napping, we've got the good side of napping, the bad side of napping. What about the tools that you can make from all this? Well, we've talked about the different types of use that you want. Striking, piercing, cutting, scraping. Beyond that, there's a huge range of variety of types of stone tool you can make. One of the most important things to emphasise, though, is that traditionally there's a difference in how we describe flint. Retouched tools versus waste flakes. Don't think like that. The waste flakes, which are not shaped, are often more used than the ones which are shaped. A waste flake has a usable edge, sharp cutting edges. You don't need to make a knife, just a sharp flake of flint will do to cut a lot of things. And if you do ever get a chance to do any microwear analysis or residue analysis on flint to work out what it might have been used on, always, always, always take a sample of what look like the waste flakes. And you'd be surprised, they will turn out to be the ones that actually been used as well. Okay. Some of the waste flakes will be genuinely waste. That's just life. But a large number of ordinary flakes are ones you can still use. Beyond that, pass that one round, pass that one round, and start with that and pass it one way or the other. You will find the vast majority of shaped tools are these things. Scrapers. Well over half the retouched tools on most excavated prehistoric sites will be scrapers. Scraping seems to have been the default activity for your leisure time in prehistory. Instead of watching television, what should we do? Oh, let's scrape. What might you want to scrape? Any ideas?
Animal hides.
Animal hides. Yep. Anything else?
Every last scrap of meat off the bone.
Every last scrap of meat off the bone. That's what your teeth are for. Anything else? not quite so obvious.
Shaving?
No, we don't do shaving. No. You need something nice and sharp for shaving. No, you can also scrape things like arrow shafts, that kind of thing. And in which case, the face of the scraper may be notched rather than rounded like that. But hide scraping is by far the commonest activity. There may be other things you might need to scrape, like reeds and rushes and things, but it's hide scraping is incredibly common. And the thing about scraping is that you need a nice robust edge scraping or pushing off, whichever action, which you can very easily resharpen. The scrapers you often get on a site are the reduced stub of something that might once have been bigger and have been gradually just resharpened. Okay. Now, all of these are ones that I've made. There aren't archaeological ones, but you could easily have found these on any archaeological site. They're exactly the same. So scrapers, get to know scrapers. Really, really common. Now, the other types of tool you can make. Well, let's have a look at some of these. So, key to stone tool diagram. A, your hitting tools, your striking tools in some way. So, axes and axe heads. Archaeologists talk about axes and adzes. What we really mean is the axe head and the adze head, because the axe is the thing with the handle. In prehistory, you don't find the handles, you find the blade. So it's not an axe, it's an axe head. Just my pedantry in there. You do occasionally find them, but not very common. And especially in Scandinavia, they've got some nice ones, actually some very nice ones. That's great. So, you can just flake a core and make it into an axe. Fair enough, straightforward. And for most of human history, that's what people did. But then when you come to the Neolithic, you find that they started grinding stones to make axes, polishing them. Now, you all know this, and this is where you start to get axes made out of non-flint materials. So go back to our geology. You need something that's hard, something that's fine-grained and will take an edge. How many of you have heard of Group 6 stone axes? Do you know where Group 6 comes from? Lake District. Do you know what it is geologically? No. It is a volcanic tuff. So it is the lava that's spewed out of a volcano, semi-solidified in the air, comes down and boom, and just concretes. Fine-grained volcanic tuff. The crystals of the minerals in it are very, very, very small, and it's really well fused together. It's very hard. Because it's very fine grained, it will produce a nice edge without flaws. That volcanic tuff in the Lake District is traded over almost the whole of Britain, especially southern Britain. Very highly sought after. And there's a big concentration of that Group 6 raw material and axes in East Yorkshire. There seem to be some kind of trade links in the Neolithic between the Rudston, Bridlington area and the Lake District. Whatever's going on, there's some two power structures there in contact in some way. So, ground stone axes or polished stone axes, axe heads, Neolithic. By the time you get to the late Neolithic and into the early Bronze Age, you have a greater ability with bronze tools to bore holes into the axe heads. So you get these things called shaft hole adze heads. What's the difference between an adze and an axe? Any ideas?
It's the way you cut with it, isn't it?
Yes.
Like, adze is that way.
That's it, exactly. An axe is cutting this way, an adze is cutting this way. The axe is what you use to cut off your branches and cut down your tree. The adze is what you use to scoop out your tree to make your dugout canoe, right? Or to shape planks. Right? Axe hammers. When they're big, they're called axe hammers. When they're small, they tend to be called battle axes. We've absolutely no idea what they were really used for, as far as I know, whether they were purely ceremonial or whether they were used. They might have been used for splitting planks and splitting wood, especially the axe hammers. Mace heads, possibly hammers, possibly symbolic. Again, shaft holes bored through the middle to take the handle, and rounded or blunted edges. The top one, A4, is commonly found in the early Bronze Age. A5 is more commonly found in the Mesolithic. So, striking tools, very straightforward. You may find sharpening flakes off the blade end of stone axe heads and adze heads. You may find the axe heads and adze heads have been reduced down to stumps and really quite small. There are some sites where there are miniature versions of these, almost as though they're like amulets, or perhaps little toys for the children, or something, or symbolic, or whatever. But there are some which are really whoppers and quite big. Cutting tools, B, very special one. You only find those basically in the Neolithic. I haven't put any scales on this, but these sickles are about 5-6 inches long. They're beautiful when you see them. They're flaked all over, curved. They would have slotted into a handle, quite obviously. So again, they're sickle blades rather than sickles, or we just call them sickles. They're not very common, very rare. But obviously, with the advent of farming and cereals, that's when you're going to get them. C, fabricators. You find them in most periods. They're a long, elongated slug of flint that's been roughly shaped into a longish lump. They're usually heavily abraded at one end. Any ideas what they might have been used for?
Nothing?
That's originally why they're called fabricators. That's what people thought, they were used as napping tools. No, they're wrong. You find them often in early Bronze Age burials with lumps of iron pyrites. They're your fire-making kit. A lump of iron pyrites, which is iron sulfide, hard metallic metal ore, hitting with a fabricator produces sparks. They're your fire-making kit. Probably worn in a pouch together on someone's belt. Now, scrapers, I put them there, D1, D2, D3. There are all sorts of different forms of scrapers, most of which are not chronologically diagnostic, except for D3. Ones which have a scraping edge which run almost the whole way round. They're quite small, they're circular in plan. They're often called discoidal or disc scrapers, very characteristic of the early Bronze Age. If you imagine D2 being slightly bigger, and if you imagine the scraping edge going 3/4 of the way round, so it has a sort of horseshoe shape, they tend to be Neolithic scrapers. D1 long end scrapers, you do find them in all periods, but if they're very well made on very nice blades, they're more likely to be Mesolithic. Right, E, the special ones, the daggers, totally early Bronze Age. They would have been slotted into a bone or wooden handle. They are quite rare, but they do crop up, especially in early Bronze Age burials. Excuse me. This is how they look like in the UK. In Denmark, as I say, you get the shape of the bone and wooden handle made out of the flint as well, as one piece. And they're absolutely incredible things, stunning beyond belief. If you find an early Bronze Age dagger, just go, whoa! They are really quite special and rare and really very, very nice. They're called daggers, but they're actually probably just knives, just everyday workaday knives. Good point and good cutting edges. F, saws or serrated blades. You find these, it's quite easy to take a flake of flint and just notch the edge to make a saw. Nothing special, totally straightforward, can be found in any period. Related to saws are knives. Now, I like knives. Knives are nice. You can do interesting things with knives. Knives can be chronologically diagnostic, but they're not always. What you've got here is some of the knives which are diagnostic. I've said that you can use any flake that has a sharp edge to cut with. So why would you need to shape specifically a knife? Sometimes the materials you want to cut are harder or bigger than you can tackle with just one small flake. They may be of a more durable material. You may be fed up with cutting your fingers to shreds holding a flake, because the back end of the flake is pressing against your fingers as you cut with the front end of the flake. So you might produce G3, a backed knife, where you deliberately shape the back and leave one end unshaped and sharp. If you think of it conceptually, it's the opposite way round to a scraper. With a scraper, you've retouched, that is shaped, the working edge. With a backed knife, the working edge is a bit that's not retouched. It's the sharp edge. Right? And the backed edge is the one you're holding against your finger and your hand to stop cutting yourself to shreds. Now, other more special ones. G4 is called a laurel leaf knife, or laurel leaf knife blade. Basically about sort of 2, 3, 4 inches in size. Sorry, I think in inches. I can't think in centimetres. I'm terribly old-fashioned. But about sort of that size. Shaped roughly like the shape of a leaf. And they usually have one edge that is better retouched than another into a smooth, slightly convex sort of edge. Early Neolithic. By the time you get to the late Neolithic and early Bronze Age, they're producing things like G1, plano-convex knives. Long flakes of flint, taken off a core in a particular way, which are retouched only on one face, into an elongated shape with a rough ridge down the middle, but quite flat, quite slim. They're beautiful things. Possibly functional, but some are so beautifully made by pressure flaking and heating that they seem to be much more for show. Characteristically late Neolithic and early Bronze Age. G2 is a type of knife in which they're made in all sorts of circular or triangular forms, and the edges are polished. They're ground down smooth, usually on both faces, into a very smooth, polished cutting edge. One of the theories for these is that these are leather-working knives, specifically for working through hides and cutting leather. Whether any work's been done recently to prove that or not, or look at the microwear, I don't know. Right. Then you come to arrowheads. We like arrowheads because they are hugely chronologically diagnostic. So, we'll start with the ones in the middle, because I'm not logical on this diagram. H5 and H6. Leaf-shaped arrowheads. Small, shaped like a leaf, may have a rounded base or may have a point at both ends. Classically early Neolithic. H1 and H2. Chisel or transverse arrowheads. The working end, again, is the unretouched edge. Sharp edge, wide edge, not a pointed arrowhead at all. It's designed for cutting, not piercing. Similar arrowheads are used today by the Maasai and other peoples in East Africa, with a very short, very small bow and arrow, which they ping into the sides of a cow's neck to cut the blood vessel to drain off blood to drink. We've no idea if that was what they were doing back in the Neolithic. These are classic late Neolithic arrowheads. I think you do get some of them in the early Neolithic as well, but they're more late Neo. They could be used for small game or for birds. But they're a different type of arrowhead to your classic pointy one. As you get into the late Neolithic, early Bronze Age, you get them being made more like H3 and H4. You find these oblique transverse arrowheads. Now, there's argument as to how these were actually mounted. I've shown these with a point rather than like H1 and H2. There's disagreement. Some archaeologists think they were just developed forms of H1 and H2. There are some like me who think no, especially H4, you look at it and it's just more obviously made for mounting with a barb on one side, as though it's a cutting point that's meant to slice through as well as and pierce at the same time. H7 and H8, your proper developed barbed and tanged arrowheads. Barb in the middle, tang in the middle, which carries the shaft, and the barbs on either side. They're mostly like H7. You will find a few developed forms like H8 and other forms, which I'll come on to later. They're classic early Bronze Age, especially associated with beaker pottery. So, coming on to I1 and I2. I've listed these as gravers because I'm English, I speak English. Most lithics specialists call them burins, because a lot of early work on lithics was done in France, and burin is the French word for engraver. I'm not French, I don't speak French, I speak English. I don't see the point in calling them by a French word. They're gravers, and that's their purpose. They're used for engraving. They're used for engraving bone and wood. And what you need to produce in these gravers is a sort of screwdriver type edge. And what you're doing is, as you can see with the little tiny arrows, they've taken the flake, they've shaped it roughly perhaps, might have retouched the back or not, but then they've taken the flake edge and along the edge, they've taken the flake off along the edge, longitudinally, to create a straightness on the edge, to take away that sharp edge. It's very hard to explain. Right? And what that does, it gives you a sort of chisel-like point at the top. And that is your engraving tool, which is good for gouging through bone and wood. Especially common on Mesolithic sites for antler working, but also found at any period as well. There's a range of shapes and forms, but they basically seem to be a very, very utilitarian tool. You'll make that edge however you have to on that particular flake. Slightly related, awls and piercers. Huge variety in forms of those. The main thing is the actual working point, which can either be retouched on one side, which is piercing, or it's retouched on both sides and it's for a twisting awl type piercing motion. Then we come to your favourite, microliths. J1 to J7. Of course, microliths are just Mesolithic, or are they? You do find some early microlith-like forms in the Upper Paleolithic as well. And there is a sort of gradation from Paleolithic into early Mesolithic. But the classic microliths are Mesolithic. J2 to J7 are your classic late Mesolithic microliths. Far, far smaller, tiny, drive you nuts. Finding them, drawing them, analysing them, God's teeth, they're so small. often geometric shapes of one sort or another. Rods, crescents, triangles, trapezes, all that kind of thing. What on earth were these used for? Well, they're parts of composite tools. You use several microliths and insert them into antler or wooden shafts in various patterns and in various ways. They're basically your Swiss Army knife of the prehistoric world. You can mount these in such a way as to give you an arrowhead, with one at the point and with barbs along the side. You can mount them in parallel down the side, or in series down the side, to give you a nice cutting edge for a sickle. You can mount them in different ways so the retouched edge is on the outside for scraping small things. You can use them for a whole range of things. Most archaeologists tend to make the easy assumption microliths equal arrowheads equal hunting. That's not necessarily true. You need to demonstrate that it's true by using microwear and residue analysis on the microliths to know what they've actually been used on. Where microliths have been found in hafts, in handles, in Denmark, they have been found as arrows. That just may be because arrows are the one thing which will get lost and deposited and covered over and will be found in 10,000 years' time. Okay. At the bottom, K1, K2, K3, these are a speciality. They're not tools, but if you imagine your flint core that you're taking flakes off, eventually you're going to hit it in a wrong way, or it will get to be the wrong shape to take more flakes off. And you have to do something different with it. You have to rejuvenate the core to make it possible to get more flakes off. So you get what we call core rejuvenation flakes. Now, if you can look at CK1, the face of it is like a single semi-dished flat face, but side on, it's got the tops of flake scars on the side. And it's the platform of the core that's been whacked off the top of the core to rejuvenate it. Okay? K2 is the face of a core that's been hit from the side to take off the whole face to rejuvenate it. K3 is more what happens when you try to make blades off a core. To make a blade, you need a vertical ridge running down the face of the core. And if you hit just above that vertical ridge, the pressure waves through the flint will carry on parallel to that ridge through the face of the core. And what will come off will be that single ridge blade, which is your first off before you take any proper blades off the core. Right? Does that make sense? Okay. So, those are some of the main types of stone tool that you're likely to come across in terms of chronological variation and sites. Now, so let me show you some things here, and we'll get into a bit more detail. So, some different types of cores. These are cores I've made. They're not archaeological ones. You'll see this flint is very grey. It's not translucent, it's pretty opaque. This was a very dark lump of chalk flint. That was one of the better lumps I managed to get out of the chalk. Very flat platform, right? Very flat. You can see the flake scars that have come off. And just by the natural processes, you eventually end up with what is a conical core. I haven't tried to make it conical, it's just what happens as you take more and more flakes off, the angle gets steeper and steeper, and you end up with you coming down to this point at the bottom. You can also tell where a hinge fractured blade came off, flake came off, so we've got the negative scar of the hinge fracture there, and there, and that, and you can see along the edges of the core, where what you do very often before you take a flake off is you prepare the edge of the core. There are little tiny flake scars where I prepared the edge to make it less brittle, so it won't shatter as I try and take a flake off. So it's like, we call it strengthening the edge. And you might do that with your hammerstone or a bit of antler or whatever. Now again, this one is very similar, although this is actually, no, this is chalk flint again, but it's Southern English chalk flint, that one. This one is some flint from the beach, from the glacial tills, and it's lovely and black. I think I heated that one as an experiment as well. Anyway, that one. Lots of flaws. You don't have to, of course, reduce a core all the way down. You may find a cobble which you've picked off the beach or the river, and you might only need a few flakes off it. And you will find cores which have just a few flakes off, like this. As that one goes round, just feel the weight and how heavy flint actually is as well on those cores. You imagine going to the coast to get your supply of flint for your napper. What you're not going to do is just bring back loads of cobbles like this in a bag. This is heavy stuff. What you're going to do is do a lot of testing of the cobbles at source. So at flint sources, you get a lot of tested cobbles to see how good they are. They may be quartered or halved to look inside and say, oh yeah, that's not got many flaws, that's not got loads of cracks, that's good stuff, we'll take that. You may find a pile of residue left from the testing, all the flint. So, right. Oh yes, just remembered, sorry. If you look at this one in your sheets, and you will have all copies of this one, there's one particular type of axe head on there that isn't on the main sheet, which I showed you. It should be towards the end, I think. Yeah, there we are. So you'll see at the bottom there's something called a tranchée axe. The key thing to note about this is the blade at the bottom is parallel to the edge. It's been struck off from the side. That's a deliberate way of making the sharp edge on the axe head. That's classic Mesolithic. Right, absolutely classic Mesolithic. You do not find that on Neolithic axe heads. Right, so that's one thing to bear in mind. Axe heads also only come in with the Mesolithic. You don't find those in the Upper Paleolithic, because it's only in the Mesolithic you had the forests, the trees. Basically, that's cutting it, that's simplifying it a bit, but basically, okay, so I'd better mention that before I forget. Okay, so we've got our evidence of napping. We might have testing waste, we might have practice napping, we might have napping deliberately on site to make tools. Let's now go to this one. So go find this one. I'm going to concentrate a bit on the Mesolithic for this, because in terms of flint working, it's very characteristic and very distinct, but it often tends to be overlooked. So it's like that one, Anne. Can you see it? There we are. You should have it there somewhere. No, so there might be. It might have been. No, keep going. Oh, unless yours has one missing. It shouldn't have one missing.
I probably just shuffled them.
Don't worry. Yeah, you should have one. I counted them all out. I counted them in. Never mind. Is there a spare one here? There we are. That's it. Oh no, that's it. Right. So, Mesolithic cores. Just like those two at the top, you can see that the flake scars tend to be elongated. They're longer than they are wide. In other words, they're blade cores. there's a tranchea axe head. You can see the horizontal axe blow across the blade. That's a drawing of a real one. But the key thing is, how do you make these microliths? You get your long blade. You have to snap your blade. How do you snap your blade? Well, first of all, you retouch a notch into the blade. Once you've got a notch in the blade, you've made a thin point, a thin section, a place where the blade is thinnest, is what I'm trying to say. Right? You can then take that notch and put it against a stone and apply pressure on both sides of the blade, and it will snap. It will fracture. You will then get the classic snap fracture. And you will get a tool, seemingly, which looks like that thing at the bottom, which originally were called burins. They were identified as the same as gravers, because that's what people 100 years ago thought they were, until they realised they were the waste from making microliths. So they're nowadays called microburins. Microburins are not a tool, they're part of the manufacturing process for making microliths. Once you've snapped your blade into segments, and you just keep on doing it into segments, then you can make your microlith by working the edges of the segments of the blade. Okay? That thing on the far right, as you look at it, that's what a microburin actually looks like in practice. Right? The sort of thing you might see on a site. Typical Mesolithic tools below: scrapers, burins, gravers, awls, saws, blades with bits of use and retouch. See how it says blade? One side it's just straight. The other side it's like had tiny nibbles taken out of it. That's probably use retouch. Again, the word retouch unfortunately is used for both the deliberate shaping of an edge and the shaping that comes from using that blade on something. Right? Because flint edges are quite fragile, brittle. Then you've got your whole range of microliths below. The first four are early Mesolithic, the second four are late Mesolithic. But that is what you would classically find on a Mesolithic site. When you come to the Neolithic onwards, flint technology actually takes a nosedive. Flint knapping becomes worse. It becomes more expedient. They're not as careful. There's some evidence in the early Neolithic in the south of England that they're still trying to make blades, but just not as well. But elsewhere, they just seem to give up making blades. They give up making microliths completely. And the whole range of tools, as we've seen with the other tools we saw, change totally. Now, if you think about it, Neolithic people, they're more sedentary. In spite of modern theories about mobile early Neolithic people, I simply don't believe it. They're more sedentary. They have less need to curate their technology around the landscape. They have less need to make the most usable edge out of their flint. They have less need to cut down the weight they're carrying. They can simply stay at home and make tools as and when they need them, from supplies they've traded in or brought in and are in a cache in a pit in the ground inside their home. So they don't take as much care. Where they do take care is in the actual pressure flaking and shaping of particular tools for a particular purpose, like arrowheads. Pressure flaking is a Neolithic development. So the way to think of it: Neolithic, early Bronze Age pressure flaking; Mesolithic, blades and microliths. And it's that kind of distinction. Okay, so right, to sum up some of that, this checkerboard sheet with X's on it. This is your timeline, your key. Now, you need to bear in mind that this is a version of something I did 30 years ago, right, when I was doing my PhD on flint tools and stuff. And what I did was I divided the Neolithic and Early Bronze Age into 6 different time periods, and using names. And I borrowed Colin Burgess's Age of Stonehenge way, dividing up the Bronze Age basically into phases. No one uses these anymore. Right, they're totally out of date, right? But I found them useful for breaking early Neolithic, late Neolithic, and early Bronze Age into two shorter periods. And what I did is I went through flint assemblages, correlated them with pottery and radiocarbon dates and whatever to work out. So just bear that in mind. Don't use these terms. People will not know what you mean and they'll laugh at you and think you're hopelessly out of date. Okay, but just for our purposes, as a way of breaking down the time. This is basically when different forms of flint tool and stone tool occur chronologically by phase. Right? So it's your basic guide. So early Upper Paleolithic, you get lots of saws, serrated tools, lots of gravers, lots of scrapers, and lots of just utilised flakes. By the late Upper Paleolithic, we get more evidence of awls and notches. Notches are sort of semicircular scraping edges, if you like. And we get tanged points and backed blades. So they're using blades and they're making a tang at one end to fix the blade as an arrowhead, probably, into a shaft. Classic late Upper Paleolithic. They disappear in the early Mesolithic and we go over to a wider range of tools. And what you'll see is the range of stone tools widens through time. The range of forms widens through time. And then by the time you get to the Beth-Branwen phase of the early Bronze Age, which no one uses anymore, the range of stone tools starts to narrow again, for obvious reasons. Bronze is now coming in and taking over. There's an argument as to how long after the end of the early Bronze Age stone tools were still being used. There is evidence for the utilisation of flint flakes as late as the Iron Age. So just because you have flints which have been obviously knapped, flints with obvious use damage on, or even bits of retouch, doesn't mean they have to be Neolithic or early Bronze Age or earlier. They could be later. What seems to happen is that the making of formally shaped tools in flint stops more or less at the end of the early Bronze Age, beginning of the Middle Bronze Age. But that informal use of flakes and blades carries on because it's just useful. You need a nice sharp edge. You haven't got the latest version, latest fashion for bronze knife. You think, oh, just pick a bit of flint. There we are, cutting, easy, you know. So when you find an archaeological site, a lot of prehistoric sites may be multi-period, but they may not. They may be a single phase episode of occupation. And you might be able to sort that out from exactly what tool types are there on this site by using a diagram like this. It might help you. Right, so that's all that side. Right, any questions on any of that?
What did you mean by formal and informal? I mean, I know what
That's okay, yeah, that's fine. Right, so formally shaped would be having a template in your mind as to this is what an arrowhead or a knife should look like as a particular shape, like a planar convex knife or a barbed and tanged arrowhead. Informal means I just need a piercing point or a cutting edge. That flake will do. Right? So you're not napping to produce a particular shape. You're just using any old flake that has the right point or working edge. Okay?